Hey everybody, this is 3J, centripetal versus linear acceleration. So it says, consider a cone made of a material for which friction may be neglected. Oh, that's nice. The sides of the cone make an angle theta right here with the horizontal plane. A small block is placed at point P right here. In case 1, the block is released from rest and slides down the side of the cone like that. It will go whoop toward the point at the bottom. In case 2, the block is released with an initial motion, so the block travels at a constant speed along the dotted circular path. So you give it a little push like that, so it goes whoosh, and it's going around and around and around, like one of those little things you put the coin in at like the zoo or the museum or the mall or whatever, and it's just going around and around and around there. Okay, so let's keep this picture handy for when we answer the next parts here. It says, in case 1, the block is released from rest. Is the block accelerating? Well, yeah, it is. Explain, and if yes, determine the direction of the acceleration. So let's look at it here. If we release it from rest, it's basically an inclined plane. So it's going to accelerate straight down the plane like that. So it's basically, we can just say it here, it's an inclined plane. And gravity will pull it down. And it will speed up as it does that. In case 2, the block is released so that it travels in a constant speed along the dotted circular path. Is the block accelerating? Well, yes, because it's going in a circle. So it is centripetal acceleration. Remember, even if the speed is constant, if it's not traveling in a straight line, its velocity is constantly changing, and therefore it is accelerating. All right, part B here. It says, in both diagrams below, the weight, F sub g, of the block is drawn. No, it's not. Anyway, draw the normal force exerted on each case in the corresponding diagram. Use the grids provided to make each normal force have the proper length. In each case, breaking one of the forces into components will help you find the direction and acceleration. So let's just sort of do it here. 1, 2, 3, 4. All right, I'm going to draw right down here the force of gravity like this on this one. So what is the other force on here? Well, if there's no friction, the other force is the normal force, which points perpendicular. So I'm going to draw it like that. So how did I know to draw it like that? I'm going to add some components on here, even though you probably don't actually want to. I know that the normal force here has got to be equal to the force of gravity, and some books call this y, some books call it perpendicular, because it's not accelerating into or out of the plane like that. So the force of gravity perpendicular's got to balance out the normal, and then this right here, we could call this the force of gravity parallel. That's the one that actually accelerates it down the plane there. What about in this case? Notice here they rotated our coordinate system like we would in an inclined plane problem. Here they kept it normal. So here we have the same length of force of gravity, because it's the same block on the same planet here on Earth, so the same force of gravity down like that. And once again, the normal force will be up here, so 1, 2, 3, 4, 5. Let's draw it like this. Now I've drawn the normal force bigger. How do I know to draw it bigger? Well, let's draw our components again. Again, it's not sliding down the plane. So now some component of the normal force in the y, I'll call it, must be balancing out gravity to keep it from moving down. And that means actually there's also a normal force in the x, I'll call it right there. So those are the two pictures that we want to have there. All right, so our next part here, part C, let me find it. So it says, derive an expression for the magnitude of the normal force exerted on the object in each case in terms of Fg, theta, and physical constants as necessary. So Fg is fine, we don't need to make it mg. So in this case right here, our inclined plane case, let's start with that one. So I'm going to say that the sum of the forces in the perpendicular direction is equal to the mass times the acceleration in the perpendicular direction, but that's just 0. So it's not accelerating into or out of the plane. What are our forces in the perpendicular direction? Normal up, FG perpendicular down. So I'll say normal up minus the force of gravity perpendicular is equal to 0 because there's no acceleration. So I'll just move that to the other side. The normal force is equal to force of gravity perpendicular. This was something you were told to memorize for the inclined plane problems. So now we just need to substitute in for that. The force of gravity perpendicular is always the force of gravity times the cosine of the angle. And the reason that is this angle right here, sorry, it's actually the way I've drawn it. This angle right, that's also the force of gravity perpendicular, and this is also the force of gravity parallel. This angle right here is always equal to the angle of the incline. Boop. So it's going to be the cosine since it's the adjacent side right there. All right, so next case here, case 2. That is for this one right here. Again, let's think about it in the y, but this time it really is more like a normal y direction here, not down the plane. But we know once again that the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, which there is none. So what are our forces in the y direction? Normal in the y up, force of gravity down there. So we've got the normal in the y direction up minus the force of gravity down, and that equals 0. So next line here, normal in the y will be equal to, so again we got to do some geometry here. If this is our angle theta here, then this would be the complement to that, and then this would be the complement to that, so back to theta, and this would be the complement of that, so this would be back to theta right there. So that's some complicated geometry there, but that's the way it works out. So, whoops, left a little mark. So the normal force in the y direction will be normal times cosine of theta, and I'm going to move the FG to the other side, and then one last line here. So normal then is equal to FG divided by cosine of the angle. Over here it's multiplied by. So part D says use the diagrams in part B to explain why the normal force is greater in case 2. Then use your equations in part C to explain why the normal force is greater in case 2. So let's do it here first. So in this one, the force of gravity, a part of it is equal to the normal force, just a component. So that means that the overall normal force has got to be less than the force of gravity, because just a part of the force of gravity can balance out the normal force. So let's just write that here. Normal has got to be less than the force of gravity because of that. So on this side here, it's the flip. Part of the normal is equal to the force of gravity, just a component of it. So here we can say the reverse, that the normal overall has to be greater than the force of gravity. Let's do it now with our equations. Come back, equations, where'd you go? Here you are. So here we got the normal is the weight times the cosine of the angle, and here we have the normal is the weight divided by the cosine of the angle. You may tend to think that that makes this one smaller because you're dividing it by a number, but remember the cosine of the angle is always going to be less than 1. So that means you're dividing by a number less than 1 in this case, which will make it bigger. Again, you can say this. That means the normal will be less than the force of gravity. Here, since you'll be multiplying by a number less than 1, that will make this smaller. So you're making this side smaller right here. So that means the normal force, sorry, I got those flipped here. When you multiply that up, here the normal has got to be greater than the force of gravity, and here the normal has got to be less than the force of gravity there.